When you hear the word radiation, what's the first thing that pops into your head? For a lot of us, it's probably images of nuclear disasters, right? Invisible dangers. But what if I told you that this very same force, when we learn to control it with incredible precision, is actually one of our most powerful weapons in the fight against cancer? Well, in this explainer, that's exactly what we're going to dive into, the amazing science of radiation therapy.
So that brings us to the big question. Is radiation a terrifying poison or a life-saving cure? And the surprising answer is, well, it's both. The real difference, the thing that changes everything, comes down to dose, precision, and our incredible ability to control this powerful force.
All right, here's a quick look at where we're headed. We're going to start with the two faces of radiation. Then we'll zoom way in, down to the cellular level, to see exactly how it works its magic. After that, we'll check out how it's used to treat cancer, look at the mind-blowing precision of today's technology, see how AI is joining the fight, and finally, peek into what the future of personalized medicine looks like.
So let's jump right into part one, radiation's two faces, and this whole paradox of such a powerful force. It really is a fascinating paradox, isn't it? The exact same kind of energy that allows a doctor to see a broken bone with a quick, low-dose X-ray can be cranked up, focused into a powerful beam, and used to completely destroy a tumor. See, this high-energy radiation, which we call ionizing radiation, is literally strong enough to knock electrons out of atoms. So it's not that radiation is inherently good or bad. It's all about how much you use and where you point it.
And that brings us down to the microscopic battlefield. How does this energy actually do its work inside our cells?
Okay, so high-energy rays, like X-rays and gamma rays, are aimed right at a tumor, and their one and only mission? To damage the DNA inside those cancer cells. You see, the primary target is the cell's genetic blueprint, its DNA. If you can damage that code, you can stop the cancer cells from doing what they do best, dividing and multiplying.
Now, what's really cool is there are actually two ways this damage can happen. The first is what we call direct damage. That's where the radiation particle zaps the DNA molecule itself, a direct hit. But the much more common way is indirect damage. This is where the radiation hits a water molecule inside the cell, and our cells are mostly water, right? Which creates this thing called a free radical. Think of it as an unstable, angry little molecule that then goes on to attack the DNA. It's like a microscopic game of pool. One is a straight shot, and the other is a really effective bank shot.
So, after a cell gets hit, one of four things can happen. First, the radiation just passes right through, no harm done. Second, the cell gets damaged, but its own little internal repair crew fixes it up perfectly. Third, the damage isn't repaired right and the cell mutates. But it's that fourth outcome, cell death, that is exactly what we're aiming for. The whole goal is to cause so much damage that the cancer cell simply cannot recover. It just gives up and dies.
And this really brings it all together. Whether it's a direct hit or an indirect one, the DNA gets damaged. And from that moment, it's a race. Can the cell repair itself in time, or is the damage just too much? The entire goal of radiation therapy is to push that damage past the point of no return for cancer cells.
Okay, so now that we get the basic mechanism, let's look at how we've managed to turn this cellular weapon into an incredibly sophisticated form of medicine.
Broadly speaking, there are three main ways to deliver radiation. The one you probably picture is external beam, where a big machine aims radiation at the tumor from outside the body. Then you've got internal therapy, also called brachytherapy, where a tiny radioactive source, like a seed, is placed right inside or next to the tumor. And finally, there's systemic therapy. That's where a radioactive substance is either swallowed or injected, and it travels through your bloodstream to hunt down cancer cells wherever they are.
This brings us to the really amazing part, today's precision radiotherapy. Honestly, the best way to think about how far we've come is to imagine moving from a shotgun blast to a sniper's rifle. Let's just look at the difference here. With conventional old-school radiotherapy, you get small doses over many, many weeks. The idea is to give healthy cells time to recover between sessions. But with modern stereotactic body radiation therapy, or SBRT, we can deliver much bigger, much more targeted doses in just a handful of sessions. It's faster, it's way more efficient, and it is unbelievably precise. So, just how much better is the sniper rifle approach? Well, the results are just wow.
They're dramatic. The 2-year success rate for conventional therapy hovers around 30 to 40%. But with SBRT, it jumps to 80 to 90%, especially for certain cancers like early-stage lung, prostate, and liver. That is a massive, life-saving improvement.
And this incredible precision is all thanks to some seriously advanced tech. You've got the Gamma Knife, which uses hundreds of tiny, weak radiation beams that all converge on a brain tumor with immense power. There's the Cyber Knife, which puts a radiation source on a robotic arm that literally tracks a tumor's movement as you breathe. And then there's proton therapy, which uses particles that basically stop on a dime right at the tumor, sparing almost all the healthy tissue behind it. This level of mechanical precision is just astounding. But what happens when you make these tools not just precise, but intelligent? Well, that's where AI joins the fight, helping us perfect our control over this incredible force. AI is completely changing the game in every part of this process. It can create a personalized treatment plan in minutes, something that used to take a human expert hours. AI can analyze medical scans with a level of precision that's frankly superhuman. It can even adjust the treatment plan every single day as a tumor shrinks or changes. And it can look at past data to predict how a patient might respond, leading to better outcomes for everyone.
But of course, bringing AI into the clinic isn't as simple as flipping a switch. There are real challenges. These powerful models need huge amounts of really good data to learn from. Getting different computer systems from different hospitals to actually talk to each other can be a total nightmare. Then you have all the important regulatory and ethical hurdles, patient privacy, security, proving the AI is safe. And there's the human element, training doctors and getting them comfortable with trusting and working alongside these new digital partners.
All of this incredible innovation is really pointing us towards one single goal, which brings us to our final section, the future of treatment and this huge shift towards perfectly personalized medicine.
This quote just says it all, doesn't it? For so long, a lot of medicine has been a one-size-fits-all kind of deal. But AI is changing that. It's giving us the power to create treatments that are tailor-made for each patient's unique body, their unique tumor, their unique biology. And the future of radiation therapy is even more exciting. I want you to imagine an AI that doesn't just look at your medical scans, but also analyzes your unique genetic code and maybe even pulls in real-time data from your smartwatch to create a treatment plan that is completely, totally, and dynamically personalized just for you. This isn't science fiction anymore. This is the future that's being built right now. So where does all this leave us? We've seen how radiation has been transformed from this sort of blunt instrument into an ultra-precise tool, now being guided by artificial intelligence. The real question now is, are we standing on the edge of a brand new era in medicine, an age where cancer treatment is no longer one-size-fits-all, but is perfectly tailored to each and every one of us? It's a pretty exciting future to